Hello, everyone. Welcome back to Physical Geology 1403. Hi, guys. Guess what? After today, you're half done. What? I don't know if applause is appropriate. It hurts a little bit, but you just want to hurt me. Okay. Yeah, thank you. Thank you for not doing that. You still have to see me after this class? Are you taking 1404? Are all of you? Ayo, how many of you are taking 1404? Yeah? Yeah? Oh, it's going to be so fun.
Even boring than this one.
Is it even more boring than this one? Ooh. You are on fire today already. Huh? I should play Magic the Gathering?
I heard you did with some of them.
Oh, I did, yes, last year. Yeah, I did. They'd bring their cards and we'd play sometimes after class. During lunch break. All right. Any questions? How was my weekend? I spent about 6 or 7 hours at the Globe on Saturday. And then did a whole bunch of work around the house, taking care of my kids. My wife was sick, so I was on daddy duty, which is, I love it, but when you do it solo, it makes you tired. So that was my weekend. Thank you for asking. Appreciate that. Anything else? You want to hold the snake? Did I feed? Oh, no. I fed Diablo 2 weeks in a row earlier this month. So this was an off week. And I will feed him again next week and again the next week. So I don't want to feed him every week. He'll get too fat. No. Out in the wilds, snakes eat relatively inconsistently. So if you feed your snake too consistently, it kind of messes up their natural metabolism and they get too fat too fast. I don't want them to get fat. I want them to maintain a natural, what's what I'm looking for? Body ratio. Okay, so I'm trying to, normally I'll feed him once every other week, but in preparation for winter, because I won't be feeding him for like 3 months, he'll go into torpor. I feed him 2 out of every 3 weeks. So he'll be going into torpor here probably in a month or 2. So I'll be feeding him 2 out of every 3 weeks from now until then. Good question. What else? I like the Godzilla shirt. Did you see -1?
I've seen some of it. I haven't seen all of them.
You should. -1 is very good. All right, no other questions? Then really quick housekeeping. All lab 1s should be graded in all of my classes as of yesterday. I'll be going through and grading labs 2 and 3 today. If you have not turned it in yet, please do so. If you see your grade and you would like to try again, you know that you can try again as many times as you want. Okay. I would urge you to, if you are still kind of hung up on lab 1, if you're kind of like, oh, that's not the grade I want in lab 1, I'm not going to tell you to ignore it. I am going to remind you, though, that you have 3 other labs that you need to have completed before the lab exam in a couple weeks. Okay, so don't get too hung up on 1 at the expense of all the others. If you've given it a couple attempts, just say, maybe I put that on the back burner for now so I can refocus myself on the other things I need to know. Okay, your first exam is this week on Thursday. That's when it opens. Yay, okay, applause for that. That's a new one. Okay, so on Thursday, our entire class session will be exam review. And this is very important. Listen up, especially my online students, because a lot of them don't seem to understand this. My exam review is entirely based upon the questions you ask. I don't have a review sheet that I give you. My class is very heavy on asking questions, in case you haven't told yet, in case you haven't been able to tell that yet, right? So the questions that you come prepared to ask, that's what will dictate the quality and length of our exam review. I've had students show up with absolutely no questions, and we stand here in awkward silence for about 5 minutes. Nobody can think of anything to ask, so I just end the review. If you think you know the material that well, that you don't have any questions to ask, then what point is a review? So please come prepared with questions. And for my online students, those of you who are watching this in preparation for this exam, please send me a list of your questions over email, not on Blackboard Messenger, over email, no later than tomorrow night, okay? Wednesday night, when I'm recording this, I should say. Anyone who's watching this further in the future, don't worry about the dates. Bless you. I will need them by that night, the night before the review, to make sure that I have them in time for the review. Because I will often show up here at the college and then drop my stuff off in my office and then instantly come in the classroom to start preparing for class. So there's like next to no time for me to check my email in there. Basically, I'm going to start the exam review, open my email here, and see if there are any questions. And if you haven't gotten to me in time, you're out of luck. I'm sorry. So please make sure you get those questions to me no later than the night before the exam review. Clear? And for those of you that are here in person, you can bring your questions in person. Where's a good place to find your questions? Your notes. If you're reading your notes and you can't fully explain something to yourself, make a note, ask about that. So you can add that to your note, a little addendum in there. You want to make sure that your notes are the best possible tool that you can draw from on your exam. Remember, you can use your notes. It is the only thing I let you use. Okay? I'll tell you more details about the exam. Thank you, Sebastian. Appreciate that. I will tell you more details about the exam on Thursday as we begin the review. Any questions about all that? Yes. Yes. This exam is just over Module 1, Lectures 1 through 7. Everything you got from day 1, culminating in what you will learn today. Just that material. No lab stuff. No identification. Just lectures. All right. Anything else? Thank you for that question.
Will it be a multiple choice or writing?
Yeah, it's a mix of what I call the usual suspects, right? Short answer, multiple choice, true, false, ordering, matching, all that stuff. Okay. Anything else? We all comfortable with the idea of our exam review and how it's going to go? Fantastic. Well, then let's move on to Lecture 7. Today we're learning about metamorphic rocks. Igneous rocks, sedimentary rocks. That's been the last couple of lectures. Now you're learning about the last type. And why do I teach this one last? Well, because you can't make it without the other two. All right? What do you see? Describe what you see in this picture.
Erosion.
All right, yeah, some of that material has definitely been weathered and eroded away. I mean, yeah, you can definitely see that. Possibly a stream bed here with a little alluvial fan out here, right? So there's definitely some weathering and erosion. Good.
It's all different directions.
What's in all different directions?
The lines.
What are the lines?
Uh,
What did we learn to call these in sedimentary rocks?
bed.
Beds, good. You're looking at these layers or beds of rock. And what was the first observation you made? They are?
In different, like different kind of positions.
Yeah, they're all messed up. We got some going this way. And then this one, these seem to be curving around. And then these seem to be curving around in that direction, right? How would you describe that? What has happened to these layers of rock?
Like they melted and they just
Ooh, but if they melted, what would they have become? No, they would have become magma, right? And then from there, they would have cooled into igneous rock. You're correct. But if it was magma, would there be any layers left? No. Any structure like layers or fossils or anything like that in a rock is destroyed when it is melted. So what would you describe? What word could you use to describe what has happened to these rocks here? They have been
like joined.
joined. I mean, they were already a unit before, right? What's the layers? I'm thinking about the layers here. Huh? Shifted. Okay, yeah. We're talking about the motion now. Shifted how? Rolled? We're getting closer to the word I'm looking for here. What happens when you take something flat and you bend it like that? What do you call that? It's flexing, sure. If I take a flat bend, okay, what's another way of describing this? Folded. That's the word I'm looking for. These layers of rocks have been folded, bent over, like so, curved, okay? You all danced around that with words for a little bit, but folded is actually the correct term here. We'll talk about that process in a moment. So, metamorphism. Metamorphism is what happens to a rock after it has received sufficient pressure and temperature to change it physically and chemically. Okay? It is remaining a solid during this time. If you heat some substance up, but not to the point where it reaches its melting state, its melting point, you will enact some sort of change within that substance. Let's go to our topic. I used this example a while back, I believe, of a chocolate bar. What happens if you heat a chocolate bar up too much? It gets melty and then you don't want to eat it. Or if you do, you're going to make quite the mess, right? What happens if you heat it up just a little?
You can see like it loses the form, the original form.
Yeah, if I were to exert some pressure on that, it would easily deform. If I take a cold chocolate bar and I exert stress on it, what's it going to do? Snap. If I take a hot chocolate bar that is melted and I exert stress on it, what does it do? It does whatever I want. It's a liquid now, right? I could take all that chocolate in that wrapper and squish it all up into a ball, right? I know it's gross. Hey, why is it gross? It's still chocolate, right? Or if I heat it up just a little bit and I exert some stress on the chocolate bar, what does it do now? It bends. Does it perhaps fold? Ah. So this is true of rocks as well. You heat them up, but not enough to be melted, and they become more flexible. They will fold. Okay? So metamorphism causes physical changes like the texture and the minerals. Okay? It will also, depending on the conditions of metamorphism, influence the chemistry of your rock. Why would it change the chemistry of your rock? Well, what's happening to the minerals that your rock is made out of? They are now being exposed to a whole new environment. And what happens to things like minerals when they are exposed in a new environment? They become, it's already a rock. I'm talking about the minerals in the rock. What happens to something if it is in a I almost said it there.
Weather.
Okay, why do things weather? Let's go there. Why do things weather at all?
Transportation.
That's the erosion component.
Changes in the environment.
Changes in the environment. Bingo. And they are no longer what in that environment? Stable. Okay, that's why all of this happens, okay? Things change, rocks weather, minerals weather, break down chemically and mechanically. Things shift their chemistry and physical characteristics in metamorphism because they are in a new environment and therefore are no longer stable. Okay? This is a repeating pattern in nature. Environment changes, stuff changes with it. You know what a good example of that is? You, and you, and you, and you, and you, and you. Why? If it gets too hot in here, what do we do?
Take off the clothes.
Don't take off your clothes. You would take off your sweater. Please take off your sweater before taking off everything else, okay? You take off, your overlayers, your sweaters, your jackets. If it gets too cold, you put them back on. Guess what? You are changing and adapting to your environment to enter a more stable condition, one that is more amenable to you. You have the ability to choose that. Minerals obviously don't have choice. It happens as a natural process, but it's the same principle. Also, on a larger macro scale, evolution. The world cools down. Things die that can't change fast enough. The things that can change fast enough survive. They become more stable in that new environment. Okay, that's a subject that we will explore a lot deeper in 1404. I'm so excited that so many of you are going to be coming to 1404 with me. Angel, you're excited. Don't deny it. Okay. Okay, so there are different degrees to which something can be metamorphosed, okay? Something can be metamorphosed a little bit. Something can be metamorphosed a lot of it, okay? We'll talk about those degrees, those different levels of metamorphism today. Something can get metamorphosed so much that you have absolutely no idea what the original rock was. It has been changed physically and chemically so completely that nothing of the original is left. No chemical trace. It's all been changed. Okay, you'll see some of those rocks later today. All right, so the causes of metamorphism. The first one we're going to talk about, heat. Yes, heat. Remember I gave you that example of the chocolate bar flexing and bending if you heat it up just a little bit, not enough to melt it? Well, again, that happens to rocks. What's happening here? If I add heat, first of all, what is heat? It is a form of what? Energy. Bingo. And as I add that energy to the bonds holding all of my molecules in place, remember, all of these are constantly vibrating. And you add more energy, what are those vibrations going to do? They're going to vibrate faster. And the faster those bonds or those molecules are vibrating, the harder it is for those bonds to remain in a solid state or in a joined state. You had too much heat, too much energy, those bonds disassociate, you end up with a liquid. You add more energy to a solid but not enough to melt it or for those bonds to disassociate, and all it does is it encourages them to find new bonds, more stable bonds, stronger bonds. Okay? So oftentimes what we will see is you'll go from smaller grains, you'll generally start to form larger grains or crystals, okay, in your metamorphic rocks. It's just more stable that way. And different minerals as well. Okay, again, larger crystals, different minerals that are more stable in those conditions. So where do we get this heat? Where are some sources of this heat? Any ideas before I flip to the next slide? The sun doesn't really provide enough heat for this process. We're talking about in excess of about 200 degrees Celsius here. If the sun provided that much heat, we'd all be in trouble. From the outer core, yeah, it originates inside the Earth. Okay, but how does it get to the surface? Earthquakes? Not really. Earthquakes aren't really a mechanism for transporting heat or energy. They are the release of energy. We will talk about earthquakes later on in another module. Volcanoes are definitely another release of energy, but that's a good point. Magma approaching the surface can provide that heat, and we will talk about that later as well, okay? So some sources. The geothermal gradient. Y'all remember the geothermal gradient? Someone remind me what the geothermal gradient is.
The melting point of the
Geothermal gradient isn't a melting point. It is, yes?
How hot something is, like depending where it is?
Where it is where?
Like underground.
Underground. Okay, so how hot it gets the deeper you go underground. The actual definition is the rate at which heat increases the deeper you go underground. Okay, so as you are going deeper and deeper underground, heat is continually rising and rising and rising. And yes, it does eventually plateau off because it can only get so hot, okay, at least until you get to the next layer in Earth. Through the mantle, eventually it plateaus off, okay? But that is what the geothermal gradient is. So the deeper you go, the hotter it gets. That means that if something gets buried deep enough, eventually it is going to reach a depth at which metamorphism occurs. Bless you.
Thank you.
Right? Now, it just so happens that geothermal gradient within the bounds of the crust of the Earth, without reaching melting points or anything like that, increases by about 25 degrees Celsius per kilometer of depth. Do you remember what the cutoff point for diagenesis was? We talked about this when we discussed sedimentary rocks. Diagenesis is any change that occurs to a sediment after deposition, but before what? After deposition, but before what? No. Weathering happens before deposition. Yeah. Yes, before metamorphism. Diagenesis is any change that occurs to your sediment after deposition, but before metamorphism. Now, the range for diagenesis happens at about 150 to 200 degrees Celsius. If metamorphism begins at 200 degrees Celsius by that definition, and the geothermal gradient increases by about 25 degrees Celsius per kilometer of depth, how deep do I need to go typically to reach the depth where metamorphism begins? 8 kilometers. Yes, it's up there. How do we do that math? 25 degrees Celsius per kilometer of depth at 200 degrees Celsius. Metamorphism starts. Divide 200 by 25, and that gives you your depth, right? 8 kilometers. About 8 kilometers deep in a typical situation is when metamorphism would begin if all we're dealing with is burial. Okay? However, there are other things that can provide sources of heat. Okay? Subduction, one plate sliding under another, provides some friction. Also provides sources of rising magma if there's water involved, right? We talked about this when we learned about convergent plate boundaries, when we learned about volcano formations. Okay? So rising magma can provide a source of heat to a local area, a small area, and that can cause some local metamorphism. Some things that can influence metamorphism through heat. Okay? Fluids. If you introduce some fluids, those fluids could contain trace elements inside of them. If you are introducing trace elements, then you may end up with something slightly different than you typically would otherwise. I apologize. I'm going to go back to my chocolate chip cookie example. Okay? Remember, I have a rock, and that rock is made out of minerals in the same way that a chocolate chip cookie is made out of all of its constituent ingredients, right? What happens, maybe Jocelyn can help me out here, if I have my nice basic chocolate chip cookie ingredients, and then I slide a little vial of dish soap to you, and then say, here, this is now also an ingredient. Would my chocolate chip cookie be the same? No, it would not. What if I slid a cup of English toffee bits to you? It would probably still be a chocolate chip cookie, but slightly more delicious in a different way, right? If I'm adding ingredients to what is available, then I'm going to end up with a slightly different result. So if my water that is being introduced to the rock, usually through groundwater, during a metamorphism process, contains some other elements in it, those elements are often incorporated into the resulting metamorphic rock. And so you'll get something a little bit different as a consequence. You following me? Great. Also, the type of rock that you started off with is a big influence, obviously, right? If I start off with the ingredients for a chocolate chip cookie and then I make a chocolate chip cookie is what I'm going to get from chocolate chip cookie ingredients. Okay? That kind of goes back even further than what we were talking about before. And that even before you start adding other random stuff, right? Dish soap. Are you still stuck on the dish soap?
Yeah.
No, I apologize. All right, that's heat. Let's talk about pressure. There are two kinds of pressure. Okay? The first one is confining pressure. Now, I want you all to stop what you're doing and close your eyes and just feel. Can you feel the pressure of the air around you? Anyone? I'd be very surprised if you could. You've lived in it your whole life. You're kind of used to it at this point. Now imagine that you're at the bottom of a 12-foot deep pool. Can you feel the pressure of the water around you? Yeah. That pressure is equally strong on all parts of your body at the same time. Your body is at that depth. You have pressure, equal pressure around you right now at our current elevation, wherever you are in the world. You're that elevation, you have equal pressure on all parts of your body. Bottom of a pool, you have equal pressure on all parts of your body. Granted, the pool pressure is stronger than the atmospheric pressure, which is why you feel it. Can't really feel this. Atmospheric pressure may have been a little bit uncomfortable when we were first born, but we got used to it quick. Okay? That's confining pressure. Equal pressure on a given point in space from all directions. This happens in the ground as well. If I were to pick a random point in Utah, 1 kilometer deep, and I just pick one random point of rock, that random point of rock has equal pressure on it from all directions. Pressure from the tectonic plate, okay? There are some places, though, where the pressure is not equal in all directions, and we call that differential stress. Differential stress is unequal force, and so instead of having equal from all directions, you'll have maybe some from here and some from there, but a lot more from here, from these directions. And what that does is it causes our rocks to deform. Deformation happens as a result of differential stress, not confining pressure. No folding or deformation will happen if all you're working with is confining stress. Okay. Differential stress pulls things, pushes things. Someone come up here and help me with a demonstration. Who wants to help me out? Yeah, thank you. Yeah, come around this way. Okay, so you take that end. We're going to hold this nice and flat. All right, and up so the camera can see it. Let's try and line up that a little better. Okay, there we go. All right, can you all see that all right? What do you see? There are 3 distinct layers here. Let's call these layers of rock. Let's pull it a little tighter. There we go. 3 mostly flat, distinct layers of rock, right? Now, currently, they are under confining pressure, equal pressure in all directions. What happens if I were to take one step toward Jocelyn? What's going to happen? How does it fold? What direction? Down and up. It is folding down and up. Down in the middle, up towards the sides. Okay? That's going to be important later. This is differential stress. I am providing stress along this plane using or where these layers of rock are, and they are deforming. How are they deforming? In what direction relative to the stress I am providing are they deforming? Well, no. There are 2 options here. Are they deforming parallel or perpendicular to the direction of stress I am applying? Perpendicular. Okay, remember that one. Thank you, Jocelyn. Appreciate it. Okay, differential stress. Clear as mud?
Clear as mud.
Clear as mud. Good. Now, do I have this up here? Aha, I do. When I apply differential stress to layers of rock, there's going to be some consequences, not only for the layers themselves. We can see what happens to the layers themselves here in this example over here. Actually, let me use a different color. Green doesn't usually show up well on the camera. Let's use black. Okay. I don't know if you can see this very easily, but if you're looking at this in the PowerPoint, you'll see it a lot better. But we're looking at layers. Oh, wow. Right after I said black would show up better. I need a new pen. Hold on a second. Where's my purple? Purple should be fine. These layers are doing a funky chicken dance. They're doing something like this. Kind of looks like a big hand the way I drew it, but you get my picture. Okay? You get the idea. They're folded and folded and refolded and folded, and this is all one big fold. What's happening here? What happened to these layers of rock?
They're folding into each other?
Yes, they are all being folded, but how many times? Too many? Yeah, fair enough. I'm looking at these layers of rock that were folded at some point in the past, and then these folded layers were themselves folded. I'm looking at potentially two different folding events here. The number of times that layers of metamorphic rock have been folded can be very good indicators for the tectonic history of that area. By kind of unraveling the folding events, you can kind of figure out, using math, which we won't use, don't worry about that, okay? You can kind of figure out the intensity and duration of tectonic events that occurred that caused this differential stress. It's pretty cool. All right, now let's look at this picture down here. What do we see here? We have layers of what once was shale. It has now become a metamorphic rock called slate. We will learn about that here in a little bit. But the original bedding planes are here like this. Those are the original bedding planes. And yet you can see in the layers of rock, you can clearly see in this picture that the rocks are breaking along those planes. Why might that happen?
One, the bottom, hold it, and then another one goes and hold it. And
Well, but these bedding planes are flat. There's no folding here.
no, but like,
Oh, I'm sorry, we can keep going.
no,
I
no,
feel like
I don't even know what that
That's
was.
okay. That's okay. No one, I don't expect anyone to know the right answer, at least not right away. That would be ridiculous.
Wouldn't there be equal pressure to one side?
Okay, so let's assume that there was equal pressure on all surfaces of this rock, on this body of rock from all directions. And I metamorphose it. Why would that explain that how my rock is breaking along planes that are very perpendicular to my original bedding surfaces? Normally, rocks will break, sedimentary rocks like this will break along the same plane of the bedding, right? Because that's the angle they were deposited in. So why is it happening at these obviously perpendicular angles?
It's going down, it's sliding,
It's sliding. What do you mean?
like, it's not like this, like this.
Oh, the beds are tilted. That is true. These beds have been tilted, but that is a tectonic process, doesn't necessarily have anything to do with what's happening inside the rock. Okay, this is fine. I'll just explain it. I haven't told you this yet. I wondered if anyone would just guess it, huh? No, that kind of has to do with what Angel was saying. There's no sliding happen here. The angle of these rocks is independent of that angle that these rocks are breaking in. When you exert differential stress on a body of rock, not only is it going to potentially cause deformation in that rock itself, in the body of the rock, it's also going to cause deformation in the minerals contained in that rock, right? Again, let's go back to our chocolate chip cookie. If I have my chocolate chip cookie and I have it right here, it's beautiful, freshly baked, just who wants to get chocolate chip cookies after this, right? Field trip to, what's the name of that cookie store we have around here? Crumble, yeah, field trip to Crumble, right? Okay, chocolate chip cookie right here, okay? Fresh out of the oven, beautiful, a little puffy, you know, I like a nice soft, gooey, puffy chocolate chip cookies. And then I take a rolling pin and go over it. My chocolate chip cookie itself has gotten flattened, but what's also flattened?
Chocolate chips.
The chocolate chips and everything else in that cookie. So when something happens to my rock, there are also things that happen to the minerals in them. So if I exert differential stress on a body of rock, that body of rock may very well be bending, flexing, doing whatever, okay? It's doing the wave, okay? But the minerals are also going to respond in some way. And we call that foliation. Sorry, my friend's calling me. He doesn't know I'm in class. Foliation, okay? And this is an example. Take a look at the large grains. This was a conglomerate. Pretty easy to tell this used to be a conglomerate. Look at the size of those, and they're pretty rounded, right? Pretty easy to tell this was at one point a conglomerate. But what do you notice about the chunks, the rocks? They're stacked in what way? Have they been flattened? They've been squished. You can tell they've been kind of squished. And you're right, they're kind of stacked on top of each other. Notice none of them are facing the perpendicular direction to the others. They are all parallel and they've all been squished. Huh?
Cementation, right?
No. The cementation happened long before when it was becoming a sedimentary rock. This is called foliation. The deformation of the minerals or grains themselves as a consequence of that differential stress. Okay? When a rock is foliated, that means that its internal minerals or grains, depending on what kind of rock it was before, remember it's made out of grains if it's a clastic sedimentary rock, its minerals or grains have deformed in accordance with the differential stress applied to them, just like this was. Now, what direction do you presume the differential stress was applied from on this rock? Let's say that this rock is oriented just like this. If I were to go out and find this in nature, I would find it in a rock just like this. What direction would you say the stress came from? Up
Bottom,
and down? Why?
because of the level of the rocks.
Is it because the rocks are parallel?
Because when squish.
Hit it right on the head, Angel. Change your major to geology. Okay? Oh, man. No, that is very correct. Why did my chocolate chip cookie squish flat? Because I squished it from the top. If I had squished it from the side, it would have squished up and down. Same thing with minerals, okay? And grains like this. Things are going to squish in the direction perpendicular to the stress applied. Perpendicular to the stress applied. So we have foliated metamorphic rocks. That is a texture. Remember we learned about about igneous textures, and then we learned about sedimentary textures. Well, now you're learning about metamorphic textures. Metamorphic textures. The first one, foliated. Sometimes you will see this talked about in papers or books or other literature. They'll refer to it sometimes as rock cleavage. I do not like that term because I have taught you mineral cleavage, and that is something totally different. So to not confuse you, I do not call it that. Okay? This is simply foliation. Okay? And there are different degrees of foliation: slaty, schistose, and gneissic, which we'll talk about. They are actually named after the types of rock that they are typically found in, the types of metamorphic rock they are typically found in. So we'll talk more about that when we learn about those rocks. Then there are non-foliated metamorphic rocks. That's pretty easy to understand. Under which type of pressure would you imagine non-foliated rocks form? What were you going to say? Huh?
Equal pressure.
Equal pressure. And what do we call that? There was differential stress, and then there was the other one with equal pressure. What was it called? Confining pressure. Good. Okay. Non-foliated rocks form in confining pressure. So now that we understand about foliation and about non-foliation, I'm going to come back to this example here. Can someone now tell me why these rocks are breaking at angles perpendicular to their original bedding planes?
Differential stress.
Differential stress did what?
The beds.
There may have been something that happened to the beds, but it doesn't have to do with the beds in this particular case. What did the minerals do?
They're squishing.
They squished, they reoriented where?
To the side, the opposite side.
Perpendicular from the forces.
Perpendicular to what?
To where the forces were being
To the stress applied. And so if my minerals are all oriented this way now, at what angle was the stress applied? 90 degrees to that. So if I'm looking at these layers of rocks and I can see those are the original bedding planes, and I see that they are breaking along that angle because the minerals have been foliated to that angle, I know at some point in the past there was differential stress applied to this body of rock from 90 degrees to that angle. And that's another little clue Another little snippet of Earth's history I can pull out and add to the tapestry that we are learning, that we are putting together. Little bits and bobs and clues that we're going to unravel. Interesting, huh? Okay. All right. And then the last texture is porphyroblastic. Porphyroblastic is very similar to porphyritic as you learned it in igneous rocks, where in igneous rocks, porphyritic was we have small crystals and big crystals all in one. It's very similar to this. You have a large crystal that grew in this case, a foliated rock, but it can also occur in a non-foliated rock. Okay? Porphyroblastic just means big crystals in with the smaller ones. In this case, a very large garnet in a type of foliated metamorphic rock that you will learn about called a talc schist. And this has mica in it as well, but there's a substantial amount of talc. Okay? Yes. Yeah, you want to see it? Oh, you wanted the snake. Sure, let me put this rock down first. You want to pass it around? Yeah, we can pass that around. All right, kid. No, he just likes my neck because it's warm. There you go. Notice that his scales are getting darker and darker every day.
Where's the other crystal? Like the garnet, you have the crystal inside?
Yeah, the garnet is the big crystal, and the small ones, those are micas. His scales are getting darker because he's going to shed here in a week or so. While he's shedding, I won't bring him out. Snakes are very sensitive while they're shedding because they also shed the scales off of their head, and so their eyesight gets really bad. So they like being secluded, you know, in dark, moist places. Kind of helps them wriggle out of their old skin. Once he's done shedding, he should be here in a couple of weeks. It usually takes him about 5 or 6 days to get all of the skin off, depending on how humid it is in his tank. It's hard to keep his tank humid in a building like this that's climate controlled. But it usually takes him 5 or 6 days. I'll bring him back out, and he will be bright banana yellow with black spots. He'll look like an overripe banana.
Do you have open snakes?
Me personally, no. He's my only snake. We have, if you go up to the biology guys upstairs, they have tons of snakes that they own. None that live here. Mine is the only one that lives on campus. I think I'm the only person on campus that has living animals here at all.
So did you like bring it from home?
Yes, their snakes live with them at their homes. But they have way more than I do. Dr. Francisco Portillo, we just call him Frank, he's upstairs in the biology department. He has a PhD in snake studies. So every weekend he goes and he catalogs snakes in our area. He's like probably the biggest snake expert in West Texas right now. Yeah.
Good thing we have him on our team.
Mm-hmm, yeah. All right. Any questions so far? No? All right. Well, let's boogie. Let's talk a little more about foliation. Foliation comes in a couple of different flavors. Okay? So you can have rotation, which is simply when a mineral reorients itself like this. Okay? No change in shape. Doesn't even really need a change in chemistry. It just does this. It reorients perpendicular to the direction of stress. You can have recrystallization, which is, I guess you could call it solid dissolution. Okay, so remember, nothing's actually melting. But if I have a clay or a bunch of clays that are no longer stable in the new environment that they have been put in, they will gradually recrystallize into a new crystal, usually a mica, that is now perpendicular to the direction of stress. Okay, so you can have that recrystallization of previous minerals into new minerals in the new direction. And then you can get that squish effect, like what happened here. Okay, I don't think I passed this around. I'll pass this around. But you can get minerals and grains. Come on, camera, stay with me now. You get minerals and grains that get squished to be flatter, perpendicular to the direction of stress, right? I'm going to keep bringing that up, perpendicular to the direction of stress. Might be important. Huh? Yeah, kitchen counter out of that. That wouldn't be bad, actually. Most of those grains are quartz, and metamorphic rocks that have been so intensely metamorphosed like that are usually pretty dang hard. We'll talk about that. Huh? Yeah, do a glass test. There you go. If you want a classic example of minerals that change their orientation and do recrystallize a little bit to be perpendicular to the direction of stress. Remember this guy? Diorite, good. Igneous rock, phaneritic, intrusive, intermediate, right? When I subject this guy to a substantial amount of differential stress, these crystals are going to do what? They're going to become foliated, right? Which means that they are going to become perpendicular to the direction of stress, which means that they are going to be parallel to each other in that direction. And you get that.
Cool.
Right? This is a type of metamorphic rock called gneiss. I am serious. Gneiss. Nice. Cue the jokes. Believe me, I've heard them all. I've also told them all. Okay. You can see it contains the same minerals. They've just been reoriented. Okay. Now let's talk about the different degrees of foliation. When I say something has slaty foliation, think of that as meaning low degree. Did it fall?
I grabbed it and I was like, huh, that looks like a little break and then it just.
Yeah, that's okay.
She broke it.
That is okay. I've got others. Now we can pass around 2 copies. Yeah. Thank you. Thank you. Big rock became smaller rock. Jocelyn is a force of weathering.
Yeah. I discovered force of weathering.
Okay, what kind of weathering was that? There are 2 kinds of weathering.
What would we call differential pressure? No?
What kind of weathering is the physical breakdown of something?
Solid.
Mechanical weathering. Jocelyn just showed us all a perfect example of mechanical weathering. Big rock became smaller rock, right? Okay. So, slaty foliation has very, very thin, straight foliated layers. Okay? Let me show you. By the way, slaty foliation commonly found in slate. Imagine that.
Wow.
I know. I wonder where the name came from. Okay. Typically very fine-grained, very thin-layered clays usually have slaty foliation. Okay, so if I took a shale and I slightly metamorphosed it, it would take on slaty foliation like this. Okay. Low grade. Think of this as kind of low grade metamorphism. In more medium grade metamorphism, you would end up with a schistose foliation. And that is commonly found in, anyone want to guess what this metamorphic rock is called? Schist. Yeah, it's schist. Okay. This is kind of middle of the road metamorphism. More metamorphosed than that slate, but not as much as we can see, as we will see here in a minute. Okay, larger grains, you're going to see those larger grains in here, and these foliated layers have kind of taken on this sort of wavy aspect. They're no longer nice and thin, no longer straight. It's because their grains, the grains in those layers have been growing. Okay.
Schistose.
Yep.
So,
Schistose
that
is the
name come
name
from?
of the foliation degree. Schist is the name of the rock.
interesting.
And then there is high-grade metamorphism. And that's that gneiss that I passed around a little while ago with the diorite. Okay? High-grade metamorphism makes a very hard, compact rock, usually with grains large enough to see, because they've recrystallized. And then not only have they recrystallized, the pressure in those directions, that differential stress has been so strong, so intense, that it actually caused those crystals to kind of get smeared a little bit. You'll notice when you look at that, you're not looking at a whole layer. If you look at a white crystal in there and then you follow it, eventually it's going to dead end. And you're going to be like, wait, it doesn't go for the whole rock. It just ends there. That's because you're looking at crystals that aren't forming layers. They're actually individual crystals that got smeared flat. Okay, think of it like that. We call that banding. Okay, it is foliation. It simply is not forming layers anymore. Okay. Now let's talk about non-foliated metamorphic rocks. Non-foliated metamorphic rocks have no foliation, obviously. They have simply recrystallized. Again, usually to make larger crystals. For example, a limestone will become a marble. A shale will become a hornfels. So on and so forth. We'll talk about all of these here in a minute. Okay. Porphyroblastic metamorphic rocks, I already passed that one around, contain large crystals, usually garnets, although starlites are also commonly found. I don't have any that contain andalusite, but that's also fairly common. Okay. So how do we go about identifying metamorphic rocks? Well, using essentially what I've already told you. Okay. We figure out what the grain size is, figure out the texture, and then that gives us our basic information combined with, if you can tell what it's made out of, that will just be the icing on the cake. Okay? If you can tell what minerals it's made out of, you're set, you're good. Okay? Those three things will tell you exactly what it is you're looking at. And if you know what it is you're looking at, and especially if you know where it was found, then you should be able to interpret what kind of rock it came from. Right? I'm not going to make you interpret what kind of rock it came from in the lab or anything. I'm just telling you that you can with the right information. So let's meet some of the more common metamorphic rocks. I already passed around slate. Okay, that slate is the big, wide, flat one. Okay, it's usually the result of metamorphosed shales. Okay, or mudstones of some kind. Yes. Okay, so the clays in these mudstones have been foliated flat, perpendicular to stress, and make those very thin layers that break off. That's why it's very common building material. We use slate a lot for making roofs and flooring because it naturally makes those very flat shapes. Okay? And just like shale, the color of your slate depends on what's in it. Red for some sort of oxide. Green includes chlorite, so on and so forth. Phyllite. This isn't one we've talked about yet. Phyllite is if you metamorphose slates just a little bit more, but not enough to make them into schist. It's like an intermediate between slate and schist. You can see it still has small, mostly microscopic grains in there, like the slate. But those layers are no longer perfectly flat. They've kind of taken on that curved shape that you will see really come to be a lot bigger, a lot more noticeable in your schist. Okay? This is phyllite. And then we've got schist, which typically is a medium grain. We interpret that to mean there was, or not medium grain, but medium degree of metamorphism. Okay, more intense than Slater phyllite, not as much as the gneiss that we'll see come later. Okay, if I were to take that phyllite and metamorphose it a little bit more, a little bit harder, a little bit hotter, that's when it would become schist. My grains have recrystallized. They are now larger. I have visible micas, maybe even some quartz in there. Okay. Usually also you've got some garnets, some starlights maybe. Okay. So there are so many different varieties of schist. Like I probably have 8 different varieties of schist just in this room. Okay. But there are so many different varieties that we literally just name them based off of what they're made out of. So if I were to look at the one that I passed around to you a little while ago, I don't know where they're ending up. Over there? Okay. Let me see that schist. Thank you. Just a schist. You can hold on to the slate. Or you can pile them over here if you'd like. If I were to look at this, I'd say, okay, well, a lot of these micas, that's muscovite mica, but I also see there's a substantial number of tiny little garnets in there. I would call this a muscovite mica garnet schist. It's a muscovite mica garnet schist. I'm literally just naming it based off of what is in it. That's the only way you can really do it when there are so many varieties. Muscovite mica garnet schist, muscovite mica garnet schist, muscovite mica garnet schist, muscovite mica garnet schist, muscovite mica garnet schist. Okay? Yeah. All right, so that's how we name these. Okay? That's how schists get their names. Then there is the gneiss. Passed that gneiss around already. Okay? It's got that banded foliation. Discontinuous layers because each layer is actually a smeared mineral, right? This happens in high degrees of metamorphism. As much as metamorphosed as you can get before you finally reach that point where you just have to melt. Okay? Usually contains a lot of quartz, potassium feldspar, and amphiboles. Okay? Sodium feldspar as well, like in the one I passed around, that white feldspar. Okay, there was a sodium feldspar. These make excellent building materials, by the way. They're usually pretty dang hard. Yes, they're very nice for building. There it is. I did it. Okay. Now let's talk about non-clastic. Or sorry, not non-clastic. Non-foliated metamorphic rocks. Starting off with our good friend, the marble. Marble is commonly used as a building material. I brought it up a few times in my class. Marble is metamorphosed limestone. Limestone's made from what? What mineral? It is a sedimentary rock, but what mineral is it made from? No.
It'd be quartz, would it?
Mm-mm. It is a non-clastic sedimentary rock, huh? Limestone. Commonly formed from calcite. It can be inorganic calcite precipitated out of the water or biogenic calcite made from a shell. Okay? Shells were made out of it and then the shells got incorporated into the limestone. Well, when you metamorphose limestone, you end up with marble. And the coloration of marble, there are so many different colors of marble, depends entirely on what else was in there with the calcite. There was a little sand in there. There was a little clay in there. If there were a bunch of fossils in there, it will affect the coloration of your marble. And the different colors of marble are valued for building materials. Statues. Why do you make statues out of marble? Because it's really soft. Calcite has a hardness of 3. So marble does too. Right? So you don't really want to build a house out of it.
So it breaks easy?
It breaks pretty easy, yeah.
Not expensive?
No, it can be very expensive. Yeah. Okay. Marble.
I saw a house, like, it's like a president house.
Uh-huh.
What's made, like, out of this? So, like, you can go, like,
You can break pieces off with a hammer, yeah.
like, sell it.
If you go to the president's house and break pieces off his house with a hammer and then try to sell the pieces, that's not the key to a successful business career.
But it is that you get found out.
It probably would not be, even if you didn't get found out. No one's going to go and just buy random chunks of marble you beat off of a hammer with or a house with a hammer. Huh?
I think you would, like.
I wouldn't. It's like, whose house did this come off of? The president. Get out!
No, it's like a house. It's a like politician, man. It's like a corrupt politician's house. It's like a hoard.
I am not advocating demolition or vandalism of any politician's house in my class. I just want to make that clear.
Are you sure?
I am positive. Okay, let's talk about the next one. Quartzite. Who wants to guess what quartzite is made out of? Ah, well done. It's made out of quartz. Quartzite is the non-foliated metamorphic rock that happens when you subject quartz sandstones to metamorphism in
Is it quartz sandstone?
quartz sandstones. Yes. Okay. So when you look at this, you can kind of see, you can still see the sands in there. They've just been fused together because of the intense heat. No differential stress here, right? Occasionally, you can see a little bit of what used to be a bedding plane, like in this one. You see that dark stripe right there? That's what's left of a bedding plane. We call that relict bedding. Okay, just a slight color differentiation right there.
Wouldn't it be a sandstone? Like, the other day when you said the sand came together and formed a rock,
Yes, that's sandstone.
wouldn't that be a sandstone?
No, because it has been metamorphosed.
So, like,
Quartz sandstone.
Yes, this is no longer individual grains of sand that have been compacted. This is one massive quartz as a result of all that quartz sand being fused together. But just like with sandstone, you can scratch that on glass, right? That purple color in there, it's probably because that used to be a red sandstone with iron oxide acting as cement. Also, an excellent building material because quartz is very hard. Oh, okay. Before I move on to that, I want to talk about a couple of these, okay? When you take a mudstone and you metamorphose it, not under directional stress, but in confining pressure, okay? You get hornfells. There's no foliation here. These are still clays, but they are still in their random orientation because they have not been foliated, okay? Hornfells. Think of this as like a brick. It's basically a brick. It's heated and compressed mud, essentially. Okay? We call that hornfells. And then when you take conglomerate and you metamorphose it, you get, anyone want to guess what you call metamorphosed conglomerate? Huh? Clay? No. What would you call metamorphosed conglomerate? If you had to come up with a name for metamorphosed conglomerate, what would you call it? Conglomer what? Conglomerphose? This is meta-conglomerate. I guess if you asked Facebook to come up with a name for it, that would probably be something that they call it. But no, meta-conglomerate. Okay? All right. Now, there are a couple of situations that metamorphism occurs in. Let's kind of start off by talking about the smaller scale ones, okay? Contact metamorphism. In contact metamorphism, you have a rising body of magma. It's made its way up through the lower crust and it's rising higher and higher. What's it doing as it does that? What is that magma doing to the rock around it? Remember I said it's not going, excuse me, pardon me, as it makes its way through. What's it doing to the rock it encounters? It's heating it to the point of melting it, right? It's incorporating rock into itself. It's hot enough to melt it. But what about the rock that it's not in direct contact with? What about the rock a little bit distance away? Heat is still radiating out from that magma chamber, right? And you reach a point where it's not enough to melt stuff, but it's still enough to do what? Metamorphose it. Now, will a rising magma chamber create any differential stress, do you suppose?
Rising temperature?
Rising temperatures, yes, but will it cause differential stress?
Wait, can you repeat the question?
With a rising magma chamber just sitting there in the crust, will it make any differential stress?
Vertically?
You say yes? Why? What about that chamber is causing differential stress on the rock around it?
Like, give me a picture. The magma rising from the volcano like this.
Yeah, well, here's a picture right here. There's no volcano. There's just a magma chamber up here. Whether or not there's a volcano is irrelevant to this conversation. There's just a magma chamber here. Is it making differential stress on any of this rock?
Yes, because it's going more to that one direction, like it's more up. Like, it's like this.
Well, the shape of it doesn't really affect the kind of pressures it could make. My question is it causing more stress in any given direction because of the fact that it's there? It's not. Okay? So therefore, what kind of pressure are we under?
No.
This rock. Confining pressure. Yes. Not differential stress, confining pressure. So we have heat and confining pressure. What textures of rock are we going to have? Foliated, non-foliated? Non-foliated. Remember, you only get foliated rocks with differential stress because that's what makes the minerals reorient. Okay? So here we have, let me grab my pen. Here I've got shale and limestone and quartz sandstone and some shale. That's what happened before the magma chamber showed up. Then this magma chamber is now sitting there. It's radiating heat. What metamorphic rocks are going to result from this? In a band, in a halo, in a border around my magma chamber, it is causing metamorphism of the original rock that was there before. It's providing the heat without introducing differential stress. And so we are going to get, what will shale turn into in these conditions? Huh? Hornfells. Not slate. It would be slate if it was under differential stress. Instead, under confining pressure, it is hornfells. What about limestone? What will that become? Marble. What about quartz sandstone? Quartzite. And then more hornfells up here because that's more shale. So we get this sort of barrier. This, we call it an areole. A border around magma chambers that has been metamorphosed. And this is a picture of one. I believe this picture is in New Zealand. I may be wrong about that. But this white rock down there, that is igneous rock. Diorite, if I'm not mistaken, from that magma chamber. Okay? And then above that, that dark rock, hornfells, I believe. Okay? Again, I haven't been here. Wish I could. Maybe someday. But you're looking at a metamorphic crown, basically, sitting on top of this igneous rock. Because when this was melted, it metamorphosed that. Pretty cool. Okay, another situation where you can get metamorphism. Hydrothermal environments. What do I mean by hydrothermal? Well, at, say, a divergent plate boundary, where the plates are really thin, water can make its way down so far. Water from the ocean, we're talking about under an ocean, okay? Water can make its way down through that thin crust and approach that melted rock. And as it does so, it will dissolve out certain metals. It will pull those metals away, keeping them dissolved in its solution. And therefore, any formerly silicate minerals that could have formed will now become a form of metamorphic rock. You get talc schists and chlorite schists and all stuff like that because you've got the heat and the pressure, but you're missing certain elements. Why? Because the water did their thing. It did its thing. Remember I told you fluids can mess things up? Remember that dish soap in the cookie? Well, what happens if I take away the flour? Am I going to end up with a cookie?
No.
No, I'm going to have a mess of baking soda, butter, and chocolate chips on my cookie sheet, right? That's not going to make a very good cookie. Well, you take away certain things. You don't make olivines. You don't make pyroxenes. You make a talc schist. Okay? So that's another way that metamorphism can occur. Okay? And by the way, what happens to those metals? Any ideas? My water that's pulling those metals away, being that close to melted rock, do you imagine it's hot water or cold water? Oh, it is so hot. It is incredibly hot water. Where does it go? Where does hot water tend to want to be? It rises to zones of lower pressure. What's above the ocean crust?
Above the ocean crust?
What's above the ocean crust?
Water?
The ocean.
The ocean?
Yeah, deep ocean. Deep ocean, super cold. Very, 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 very cold. What happens if I take superheated, metal-rich water and I introduce it just like that into super cold ocean? What happens to those metals? Instant condensation and precipitation, okay? It is going to, this is called a black smoker. If you've ever seen like a National Geographic or Discovery Channel documentary about the bottom of the ocean, they will always show you these, okay? It looks like smoke spewing out of the Earth's crust and into the ocean. That's not smoke. That is metal coalescing in the cold water, precipitating out as tiny little metal crystals, and then filtering down to the bottom of the ocean. We talk about these a lot more in 1404 because it is around these that we believe the first chemosynthetic organisms began long, long, long ago. Also, these are very relevant for mining operations, perhaps in the future, not right now because they're really deep underwater, because we're talking about literally millions and millions and millions and millions of years of that metal just building up on the bottom of the ocean. All you got to do is scrape it off and look at all the metal you've got, right? That's a conversation for another day. Another way that you can get metamorphism to occur happens at plate boundaries, subduction zones, okay? Here we've got our subducting plate. There will probably be some metamorphism here where they scrape past each other because of the friction heat. But then the deeper you go underground, the more water you introduce. That's where you bring up the melting point, and you get your plumes of magma rising up near the surface, okay? Also, it is these convergent plate boundaries that typically will cause a lot of differential stress. The intersection, the crashing effect of these plates running into each other will create a lot of differential stress. The Himalayan mountain range, a lot of metamorphic rock. Because imagine the incredible differential stress pressures of these two plates, trillions and trillions of tons of rock crashing into each other. That incredible stress causing all that deformation, making those mountain ranges, okay? And then you've got basin burial. So like out here deep in the ocean or out here on a continent, as more and more sediment gets piled on top and what was on the bottom gets pushed deeper and deeper and deeper, eventually it's going to reach metamorphic conditions. Regional metamorphism is what I was just describing with the whole India-Eurasia situation. It's where two plates crash into each other, and that violent, I mean, this is happening over millions of years, but you know, the amount of energy that's released, I think I can call that violent, okay? Over all that time, all that energy causes massive deformation and foliation, okay? In a very large area. Regional metamorphism happens over a large area. You can see that easily, so easily from space. You could see it from the moon, right? You can see the Himalayan mountain ranges from the moon. You can see that massive regional area of metamorphism, okay? Some other situations of note that can cause metamorphism. Faults. We haven't talked a lot about faults yet, just a little bit in lecture 1, and then we'll talk about them a lot more when we discuss earthquakes. For now, just know that a fault is essentially a crack in the earth caused by some kind of stress. And along that crack, stress builds and builds and builds, and it releases, and that's when you get an earthquake. But while that stress is building, it can cause some metamorphism along the plane of that fault, of that crack. Okay? Fault zone metamorphism. Usually it will make some sort of like shattered rock compress into a new metamorphic rock. We call that a fault breccia, usually. Okay? And then the other very interesting situation that can cause metamorphism, impacts. Asteroid impacts, meteorite impacts.
Whoa.
Imagine this, okay? A 200-pound rock hurtling through the atmosphere, striking the ground. What's it going to do? 200 pounds of mass, 200 kilograms of mass, I should say, not pounds, that's weight. 200 kilograms of mass slamming into the ground. What's it going to do? It's probably going to melt it, actually. That's an incredible amount of energy. The impact of two bodies like that, something's going to melt. The smaller one's going to melt, but it's also going to make a small area in its crater melted. Even if it's only for a brief instant, it's going to have a melted zone. And all the energy and heat from that impact is going to radiate outwards. And it's going to make an impact crater. But around that crater, that heat and instant pressure is going to, just for a fraction of a second, metamorphose the minerals in that rock that was there already. Okay? We call these impactites. Metamorphism caused in that circular shape around an impact crater. And if you guys ever been to the Odessa meteor crater? No? It's only a few miles out of town. You haven't been there? It's not a whole lot to look at, I'll grant you. From space or from the atmosphere, you can definitely tell it's there, but then you walk around and you're kind of like, where is it? Oh, you're standing in it. Or it's just right there. It's, oh, that's it. But it's a meteor crater. It's pretty cool. Okay? There is a zone of slightly metamorphosed rock around this crater from when that happened. Okay? All right. And then the last thing, or not the last thing, second to last thing. So the closer you are typically to your metamorphic situation, in this case, in this diagram, it's a regional metamorphism situation, okay? So two continents have slammed into each other. Think of this as a sort of Himalayan situation, okay? The closer you are to it, the higher the grade of metamorphism is. So if I have the same layer of rock out here on the periphery of this zone, and it's only getting a little bit of metamorphic, a little bit of differential stress, you're going to end up with a slate. Closer to the actual source of this stress, you're going to end up with a phyllite. That same layer of rock further in is going to be a schist. And then down here, deep in the heart of this mountain range, where the stress is as strong as it can get, that's where you form a gneiss. All from the same layer of rock, just under different conditions. Okay? That's what I mean by degrees of metamorphism. And then finally, depending on the situations, the temperature and the pressure, you may end up with different types of minerals that form, right? So chlorite, muscovite, and biotite, very common in a lot of these metamorphic rocks. Things like garnet and starlite and sillimanite, those tend to occur only in the ones on the further end, okay, from schist on usually, okay? And then the last thing I want to talk about, remember our discussion about partial melting in igneous rocks. You remember that? Some minerals have a melting point that are higher than others, and so if I only heat my rock to a certain degree, some things will melt and other things won't. What happens if I do that to a metamorphic rock? Let's say I have a schist, and my schist has quartz, feldspar, and amphibole in it. Let's say I heat that schist up to the point where the quartz will melt, the feldspar will melt, bless you, but the amphibole will not. What do I get? Well, I get this. This is a migmatite. I partially melted my gneiss. I now have still foliated, folded layers of amphibole that never melted, never changed. They didn't get that hot. But the quartz and the feldspar did. And then when I cooled that back down, what did my quartz and feldspar, what did the magma from the quartz and feldspar cool down into? Quartz and feldspar. However, they are no longer metamorphic. They are now igneous quartz and feldspar crystals in between the layers of metamorphically foliated amphibole. I think that's pretty cool. You can see the quartz and feldspar in this thing look like what you would see in a granite. But you can clearly still see that the amphibole is folded and foliated from the metamorphic process.
So it's when a rock is metamorphed, but the inside got melted, some of the rocks in the inside got melted.
Yes, this is the partial melting of a gneiss. I'm still calling it a metamorphic rock. The debate as to whether or not it is more metamorphic or more igneous, that's something that isn't necessary to go over in my class. Most of that rock is still metamorphic. Okay? Be careful when you hand it to Jocelyn. I'm kidding. I'm kidding. All right, any questions about our lecture today? No? Okay, well then let me really quickly introduce you to Lab 4. This is the last of the identification labs. Now clapping is appropriate. All right. This is really quick because I went over most of this in class, okay? So you're going to be identifying, is it foliated? And there are several different types of foliation that we discussed, right? Stretched grains, that's squished, that's another type of foliation. Non-foliated, you can have recrystallized grains like marble. You can have fused grains like quartzite. And then different things can form. You can have clays that become micas. You can have porphyroblastic things like garnets and starlites. So how exactly do you go about identifying what your metamorphic rock is? Find the texture. Try and identify some of the composition. Okay? Even if you can just positively identify one mineral in there, it will help. Okay? And then a few other things, which you'll see on the assignment, that aren't on this diagram, but you'll see on the assignment, okay? That'll get you in the right direction, and you'll be able to find your rock name. Same thing as with all the other labs. You'll use your Excel spreadsheet for those of you that are here in person or that come in later in person at another time. Use the practice samples at the back of the room, okay? So, is it foliated? If it is foliated, does it have layers? What is the grain size or crystal size in your rock? What are the dominant minerals? I'm asking about the composition. And then finally, what is the metamorphic rock? That's the lab. Any questions? Okay. Lab 4 is assigned. If you're still working on Lab 3, go ahead and finish that up today. And you can, you have, let's see, this is week 4. We do the lab exam week 6 or 7, I want to say. It might be week 7 by the time we get to it, depending on, it varies semester to semester depending on the holidays we have during that semester. But it'll be either 6 or 7. So you have a little bit of time to catch up and redo labs if you want. But definitely don't ignore other assignments to try and make up for a few points on a lab. All right, I'm going to end the recording here.